So the to appreciate the differences there, in the foreground window, which is the Cloudera Quick Start on the right hand side, if I just do ls right here, I'm going to see some set of files. If I do ls-l, it'll be a little bit more interesting to be able to see. Those files are all within where? So this section here is all within Linux, and on the whiteboard, where did I draw that?
What's the question?
So this set of everything that I just did ls on right here within the terminal window of the virtual machine, it's displaying files from where? One of these 3 points. Right, it's displaying from the file system managed by CentOS that is /home. So root is / and then home is a directory underneath there. Okay. So within this file system, I cannot get to anything over here. So if I'm under users here, and I just do a dir listing, this window which is brought up in Microsoft Windows is a completely different space than this one over here. Okay, so what file is over here on the left that is associated to what's on the right?
I cannot see the.
Okay, well, this is more conceptual because the answer is not on any of the lines here.
Oh, okay. The file access table, the listing, the file list, file listing is.
This is the bare computer, the host computer, that
Right,
one.
the black area is the host computer.
Host computer. The white one that you have there, that's the virtual machine file system.
Right.
Oh,
And if I go in the background then, and look exactly the way Juan is describing this is perfect then, if I go over to this other window and do the dupe fs-ls right here, and might slow that out too.
Slow too. So it's not.
So in here I see the test directory that I created earlier. And I can put in a path here that says ls user Cloudera, because the /user is only known inside the file system that is HDFS. So it has no problem recognizing that. If I go over and say ls user Cloudera, take that command, put it in the background. This is where I gotta fix the pasting here. User Cloudera. It's gonna come back and say, what are you talking about? It doesn't exist here. Because what does exist over in the CentOS file system is only home Cloudera, not user Cloudera. So that in the same way that Juan started out saying this black region on the left, that's your C drive, your guest, or sorry, your host operating system file system view has one file that is all of this blue space. Within this blue space, which is the virtual window, I've got my Linux CentOS file system. Within this file system, I do have HDFS mounted. Okay. So in order to look inside HDFS, I have to put in this command ahead of time that what is Hadoop space FS. So this is what's referred to as a virtual file system. mean, the only way to look into the virtual file system is to use the command line interface, in this case Hadoop, under space FS, is the command line interface to look into this virtual file system. So I've got a virtual file system inside a virtual machine that's inside a host environment. So there's depth of 3 layers. And going back to the PowerPoint here then. The whole point of this first lab is to get comfortable with that concept. So any other questions related to that? And as people are asking questions and about, well, why don't they see dot trash or dot staging or dirt 2 in there? It's just because this snapshot in the slides is not a snapshot taken after installation. Okay, if somebody had worked on that in that virtual machine before you, potentially you would have seen this information. All right, so any other questions associated with just HDFS, copy to local, copy from local, just getting comfortable with the virtual machine environment here.
What is the mount point of the HDFS on CentOS?
Yeah, CentOS. I would have to look that up. I don't remember what the mount point is. It wasn't mentioned in Hadoop book either. But there is a mount point where that file for HDFS is located somewhere inside of the root directory space here. The way this is root right here, I do ls, do the long view. This is everything that's mounted under the root directory or present under the root directory for CentOS.
There's no doubt the HDFS idea.
Somewhere under here, there will be a mount point for HDFS. I don't know where it
But
is
you can't
exactly.
access HDFS directly, right? You can only access it through the HDFS command.
Right, only through the CLI, command line
If
interface.
you know the mount point, you should be able to. If you don't know, then you cannot.
Right, so it's configured and it's part of the environment variables. There's a set of environment variables for Hadoop. So we can look at that in detail later. So any other question on working with the file system? So I'll mark down that one. Is, where is the mount point exactly? I haven't looked at that in terms of what Cloudera provides for a quick start configuration. Okay, so with that said, sounds like there's a nice pause. Let's go into the LinkedIn case study here. Had that sitting in the background for a little bit.
The copy from local command, you're actually copying from your local CentOS to the Hadoop file system, right? Can you do an example of that?
All right, so if I do touch a file called test file like this, so this is in Unix, you can just create a 0-length file using the touch command. And what was that you asked? Dinesh?
Copy from local.
Copy from local, which means to FDS, HDFS. So then take that file, go ahead, what's the rest of it? From local, test stuff. I could just go like this, copy it straight out. To help cognitively keep this straight here, I'm going to put these two windows one above the other. Find it. Okay, so this bottom window is all the commands that are going to be associated with the Hadoop file system. So if I just do ls right now, you can see the test file with a 0 length. You because I didn't put anything in it. So here's the test dot file with the 0 length, and I know it's a file because when I look over here, it's got a dash in there next to the permissions instead of a D. Okay. So if I, within Hadoop, if I'm putting in some content, I don't even remember if this is a supported command right now. I'm just going to take a while to guess at it.
Yes, sir.
Let's say test file 2.
Should you do an echo, dash echo? You should do a dash echo.
Yeah, I forgot that part.
Dash.
I don't know if I can support it or not. Yeah, it's not. It's a subset of the commands.
Actually, you can do a
If you do a,
content redirect to HDFS.
if you do Hadoop FS, it lists the
Possible
commands there.
Yeah, all possible commands would be listed if you just do Hadoop. Space FS. So there's a nice long listing. Echo is not in there. I haven't typed Echo in the past, but it was quick enough to just try it. It'll tell me whether it's supported or not instead of looking at help.
You can only append to the Hadoop files in the Hadoop system, right? So that means maybe you can only.
Oh, actually, that, you just mentioned the answer. So the equivalent for what I'd normally do in Unix could be done with the dash append to file. But that assumes I need to use local source and destination. So I'll mess with that later because I don't, otherwise we won't have time to get through these other slides.
Okay, that's fine.
So the idea of this is in home, get Caldera installed. We've seen mixed results here. In March, everything was fine, and then those machines got shuffled around, so I'll try to unwind that problem. But on your machine at home, you should be able to do pretty good. I haven't run into problems with my machines at home. The Kegels will figure out, let people know what happened on that machine. So try this on yours. See what happens. I know you got yours here, Joe. Are you able to get yours?
I need to enable the virtual machine on the BIOS.
Oh, yeah. So yeah, that for some of the installations for HP machines, virtual machine has to be implemented in BIOS level. So there's a little note for that. That was in the instructions. All righty. Let's go look at. There we go. All right, here's a set of slides. I can send you the link. This is from 2015, but it's a really good portrayal of big data in a commercial case study context. So I'm going to take us through this. And I might have to step off the glass of water because this is running low. And I haven't been drinking as much as I usually drink in one day. That's okay. I want it to be full screen. All right. So. In 2015, LinkedIn had 360 million members. They're adding 2 new members per second. All right, so high growth. Okay. There's a large number of products in here that they identify as their products. The application specifically that this case study focuses on is the people you may know. There's a lot of other items in here. There are applications like jobs you may be interested in. Up here, Talent Match in the middle, CAP, I don't know what all of their acronyms are. but there's similar jobs down here at the bottom. So if you think about the LinkedIn environment, each one of these items in the grid, in this 3x3 grid, these are 9 separate applications, and they're utilizing connections, they're utilizing or taking into account news or similar profiles or endorsements. So that the stuff in the left panel here, you can think of as different data sources. And over here are various applications that use data sources. And also write to data sinks, which may be the same as the source, depending on what the nature of the application is that's operating. All right, so they, basic process for building their data products, because they're obviously nothing more than a data crunching company. I wasn't right on my memory here. Egress is the other word. Ingress and egress, those are the 2 words that are common in certain domains. You see those showing up in big data that's present in computer networking type circles heavily. So nothing new here, nice and simple. Here's all of LinkedIn Business's IT infrastructure summarized in 3 bullets. But the complexity is behind the scenes. It starts with this front end where they have the data ingress from their front end going into HDFS, showing data processing by PYMK, which is people you may know. I'll just say the people application for people app in order to make it a little less wordy. I'll try to say that 10 times. Sometimes I'm going to trip over this eventually. Okay, so there's egress there's a Voldemort. It's a special database that LinkedIn has put together from, in terms of the schema and content. All right, there's a back end, not just the data processing front end here that cleans the data, looks through the data, and then sends the results into Voldemort. But there's also a back end that writes into this space as well. So I don't know all the full details on all this. Some of the stuff I'm going to skip over because my intention is not to go through each of these slides, to hit the main points. We'll see a pig script coming up in here that I really want us to be able to focus on. All right, so data ingress, moving data from online to offline systems. Let's take a look at that. So types of data, they got member profiles and connections coming in. You got activity data in terms of page views, got service logs, application system metrics, 4 high-level categories. Nice clean categories. Here's the mess that they encountered. You take all of their databases and applications as well that are indicated by the services over here. You try to get them all talking with each other in the way that they they have dependency on each other. You need to create a separate extraction of information from like Espresso into each of the applications that are using Espresso. And each of the applications using Espresso would have to have a special import of data from Espresso. So you have the specialized export out of Espresso to each of the consumers. You have the specialized import from Espresso associated with each of these consumers. So that's a lot of software getting rid of. It's a mess. Okay, so no standardization, it's fragile, delayed. All right, so here's the concept. This is the concept that birthed Kafka and Kinesis. So Kafka is from LinkedIn and was open sourced by LinkedIn. It functions the same as Kinesis, which Amazon created. So instead of having that mesh, which you saw in the prior slide, you have this really clean interface where each of these potential sources are writing their event cell into a log type format that is this data pipeline. And that log format gets read by any particular consumer that's interested in information from one of the providers. So you have providers on top, consumers on the bottom. This doesn't mean that the consumers can never be providers. You can have consumers and providers at the top, consumers and providers at the bottom. This is just the oversimplification to illustrate the point that you can flow the information into consumers down at the bottom. You do see a couple arrows here at the top that are bidirectional, meaning these are places to write into from other locations. All right, so from an ingress perspective, this is where Kafka got born. So Kafka, if you break it down then, Kafka is this data pipeline solution in the middle for messaging purposes. So Kafka is based around publish subscribe messaging, which is not anything new. It's been around for a long time. It has a slightly different twist to it, but the idea of subscribing to a message queue and the messaging service waiting until you as the subscriber have read the packet of interest, that's been around for a while. So publish subscribe is not new, but they do use it. So producers send messages to a broker. So here's where Kafka comes in with something new. The broker is going to take and organize the messages from the producers. They're going to organize it around a schema that the consumers can interrogate in order to see what information is available. So in order, the consumer 1 and consumer 2 can discover what information is available by going and looking at the schema that the brokers provide. All right, so this is showing consumer 1, consumer 2 more as a snapshot in time, meaning that consumer 1 can have multiple readers set up to read from the brokers. So consumer 1 is reading from every broker. Consumer 2 is organized a little bit differently in that it has this component here that's reading from 2 brokers. So this idea of 1 broker to 1 consumer is not a restriction. It's more of a capacity issue. If there's a lot of traffic, I might need 1-to-1. If there isn't a lot of traffic, it's okay to have a couple brokers associated to 1 consumer. So the multiplicity is flexible. Right, so that's the point of consumers reading messages from brokers. Messages are sent to a topic. So I mentioned the schema. The schema is a set of topics. A topic could be people you may know. Each topic is broken into 1 or more ordered partitions of messages. So you get a topic, and then there's a partition that's ordered, and it's ordered by time. Okay, so the consumers can look at what they're interested in from a time perspective. There is no other way to slice the data except by time. All right, so a standardized schema for each topic. They use Avro. So we mentioned the different file formats. Avro comes in here as what as a means of expressing the schema, i.e. the topics. There's ETL to Hadoop, which is interesting because wait a minute, since when do message services write to Hadoop? Okay, so Kafka is using HDFS to store all the messages. Now, any type of robust messaging system always stores its messages to disk to ensure that the consumers will never miss a message. So Kafka does the same thing. Okay, I should mention that the big difference with Kafka is that it never deletes the message after a consumer reads it. So the trigger point for Kafka deleting a message is age. If the message has been stored for say 30 days, then it'll go out and delete it. Okay, so it's configurable whether it's 30 days, 60 days, 10 days, whatever the company wants to set is the lifespan for that message, they can set it. So this notion of the consumers reading the slides, I don't speak to this tightly right now, I know, but let me go back to this slide here. The fact that Kafka, under the scenes behind this broker, is storing these messages means that it could care less whether all of these consumers have read a message that was sent at a particular point in time. like 6 seconds after midnight on the 23rd of a month. Kafka really doesn't care if the consumers fail to read it or not. It's the consumer's responsibility to go get the message. If it wants it, Kafka just says, I'll let the message hang around for like 30 days. If you want it, come and get it. So that's the opposite of normal other messaging services, because other messaging services are all organized around the idea that I don't have enough space to store the messages. So as soon as a consumer reads the message, it deletes the message. All right, so instead of this almost instant delete, there's this perpetual store for up to 30 days. Because now storage space and the processing that Kafka requires is a very low cost commodity. It's using HDFS for all of its storage. All right, so that's the main point with Kafka here. We'll be able to touch on that a little bit later. From a data processing perspective, this is where we get into PIG and other aspects. There's high-level map and reduce functions. So map just means go find the data on all the data nodes, reduce, take that data which has replicas, so there's over information, too much information, and reduce it down to what the client actually needs. And we'll look at MapReduce next Saturday. Right, so Hadoop itself is scalable to a very large cluster, fault tolerant, etc. So this is the processing environment for the data that's getting stored. The front part about this, about being scalable to a very large cluster and fault tolerant, that's true for Kafka's needs, and Hadoop provides that from an HDFS perspective. Scripting languages, Big Hive, Scalding is another one out there that is not as commonly present. So if we look at Hadoop just at LinkedIn, they're trying to characterize how do they use Hadoop. Okay, so if you look through these bullets, it's used for data products, future computation, training models. So what's a training model? For the big data analytics class, what is a training model used for?
Certifications.
Not for certifications. So this is like, wait a minute, I thought we could forget about analytics. The whole point of the analytics is that it uses the data. It has processing requirements on the data. So LinkedIn is focused heavily around their analytical needs. And you'll see that pop up in a few slides as we go through here. So a training model means that some data scientist or data savvy person is wanting to tweak their prediction model. So remember, a model is always used for prediction. If you do a simple linear regression and your current status data is now, and you're doing a prediction into the future, how much am I going to sell in the future? Under what conditions? So anything that brings together multiple variables or even just two variables is described mathematically as a model. So when it says training model here, this is the data pool that's being used to confirm how reliable a mathematical model is in predicting whether people are going to click on that link for a potential new job, for example, the jobs you may be interested in. You want to be able to predict, are they going to click on that link or not? What percentage of the user base in LinkedIn is going to click on it? Where LinkedIn is going ahead and using a huge amount of resources to try to get people to connect with each other in a first level connection relationship. So they're very interested in, okay, should we just give up on this person and say, use LinkedIn like once every 6 months? In which case the training model says, if you're only on LinkedIn once every 6 months, they're going to just omit you from their processing. Because they're just burning up CPU cycles and storage over somebody that's really not participating in the LinkedIn community. Okay, so they have to balance their resource of machines and storage relative to the potential for somebody actually taking action. So a model is a prediction of will the person take action or not. In this case, it's a people-oriented thing as opposed to forecasting inventory changes over time. All right, so native MapReduce is used. So this is just meaning MapReduce version 2. Big is used, Hive is used. All right, Big is a scripting language, Hive for SQL. All right, so this is interesting. So there's workflows. So what is used to create workflows? Yeah, Woozy, right? So we get that in our minds. So next Saturday, come back and ask the same question. Go, Woozy, right? Okay, so there's workflows, meaning each, and it's hard to read this because I didn't author it, obviously. But I think the way to read this is that out of a set of workflows, that set of workflows involves hundreds of Hadoop jobs. Okay, so hundreds means somewhere into the low thousands aggregate if you look at it cumulatively. So there's hundreds of workflows generating, I would say, thousands of Hadoop jobs, not just hundreds. If I had hundreds of workflows, I guess say that I had hundreds of Hadoop jobs. All right, so much data processing. It's expensive. All right, so there's a few slides here on this first, second, and third level connections data model, on which the people you may know features working on trying to close those triangles. So Bob knows Alice, that's first level connection. Alice knows Carol, first level connection. That means Bob to Carol is the second level connection. And LinkedIn is trying to encourage people to say, well, hey, Bob should ask Carol or Carol should ask Bob to be a contact so that it can be a triangle of first level connections. First level connections is their goal, so that they can proliferate data so that recruiters that have accounts on LinkedIn can find people a lot more easily, and people with certain skills as well. All right, so there's this idea of closing the triangle. All right, so what does this look like? Here's a pig script. So let's go through this. This is the entire pig script that runs. There's more about it over here. So it's easier to look at this and then go back to the script. All right, so if you look at this as a graph where every circle is an individual, this is a graph of who knows who. Who's connected to who in a first level connection perspective. All right, so you've got to be able to manage the production Hadoop workflow. The workflow is oriented around traversing this graph, coming up with people you may know that are second level connections. All right, so in order to traverse that graph, they have a simple paradigm here. Big is a data flow processing paradigm. It's not a declarative language like C or C++ or Java or anything like that. So it's data flow oriented. The first step in that flow is some type of load command. Okay, the next step is going to be a group or filter command. Here they're just doing a group command. And I'm purposely going down this vertically, looking at what, from a pig perspective, is referred to as operators or operations. So the keywords here, they say are operations on a tuple. So that, yeah, connections becomes a tuple. Or sorry, becomes a relation. And the relation is the tuples. So after every line of code, I have a relation that's generated. All right, so the language of working with Pig is interestingly unique, but fortunately it's not overly complex. We'll get into the terminology. If you looked into your slides a little bit already, you've seen some of these terms pop up. All right, so load group for each. All right, so if I pause on the for each, obviously that's a for loop, just walking through every member that's in that relation. There is no if statement, if then else type statement structure in Pig. There is no while loop in Pig. If those control structures are needed, then Pig can be embedded in Python or Java. So that's the way that works out. Let me say that again when we do the intro to Pig slides for Pig Lab next Saturday. All right, so load group, and I said group or filter. Okay. So group is the same as an oracle. We're trying to group people by city, or group them by country, or group them by whatever the criteria is. Group by first level connection versus second level connection. All right. Walking through the for each, I get a tuple called pairs that comes out of here. So the second degree pairs, ID1, ID2, aggregate common count connections. All right, so pairs is second degree pairs. So this is if Ganesh has and I were first level connection points, that means that this script would give him my second level, my first level connections, because they are second level to him. And this script here that we're looking at would give me his first level connections, which to me would be my second level connections. Okay. And so I get these second degree pairs that come out of here. And there's more grouping done. We're not going to walk through all of this from what is this doing exactly for the people you may know. So I'm more interested in the total logic here. There's a group process of for each, and then group again, do a for each again. The flatten here takes out schema. So one thing that's really interesting about Pig is it requires no schema. Or I can have the schema present. So this load command, if this said load as, then I would, in the as clause, I would be specifying, oh, this is the name of the person, this is the person's phone number, this is the person's company name, this is the person's country location. So it, as a part of doing the load, that's when the schema gets defined. Okay. Right now, using Pig storage though, this is just reading in a tab delimited file of text. That's what it's going to be read in. When we go through the grouping and everything here, it takes the schema and builds on it. It's just column names, it doesn't mean a lot. This flatten in here says, get rid of all that extra schema stuff, I don't need it. I just want to figure out the common connections in here that are plausible and then store it. All right, so load, process, meaning group for each, maybe group again for each, and then store. Okay. So this looks a lot like a SQL script in one sense. And if you're writing SQL in a relational database environment, the SQL engine will go behind the scenes and build a plan relative to all the statements in that SQL script. Or actually even in the SQL statement itself. So the similar thing is happening here with Pig. When Pig is being run, it's going to build a logical plan that's going to be built for the statements here. And that logical plan is all organized around where do I need the map job? How many reduced jobs do I need? Where do the reduced jobs fit in relative to the lines of statement here in Pig Latin? So that the language that's the name of this language here is Pig Latin. So this is how simple Pig is. But it'll take us about 3 hours to go through and appreciate what's happening in doing this. Because the last class I went through on this, we did the lab first and then looked at this. People's eyes all of a sudden lit up like, oh, I actually understand everything that's on there. Okay, but in order to get to the point of understanding everything that's on here, it takes about 3 hours. Like I said before, it's like the broadness is wide, but the depth in terms of the complexity is really shallow. This is very shallow. There's not a lot of lines of code here. Okay, the graph we took a look at. All right, so Azkaban is what Hadoop uses instead of Oozie. So there are several workflow orchestration tools. Azkaban provides what the 5 bullets are indicating here from a general perspective. They have a machine learning viewpoint, which is artificial intelligence. On the very bottom here, you see analytics popping up again. Okay, so we talked about regression in the analytics class. We don't get into all of the details behind all of the different regression models that are out there, because there's dozens and dozens. From a categorical perspective, there's something called logistic regression. So logistic regression is a binary response prediction. It's like, is that person going to say yes or no? So in order to come up with this predictive yes or no model, there's a technique called ADMM. So this model works based on partitions of data, each being separately treated by the model. So I have 4 plus however many additional treatments of the data shown on this slide. The results of that treatment is a consensus computation, meaning that what's the sum of the positive binary responses versus the probability of error that is it 80% chance that 90% of the people will say yes, or 50% chance that 2% of the people are going to say yes to whatever LinkedIn is throwing in our face, trying to invite us into other relationships or job opportunities.
So it means that it must have only 2 possible paths, 2 possible solutions?
Yeah, 2 possible outcomes.
Outcomes.
Yeah, logistic regression is only 2 possible outcomes.
Only 2 possible outcomes.
Yeah, it's like true or false, yes or no. As opposed to linear regression, which is more for continuous numbers. If I want to be able to predict population growth, linear regression is going to give you a range of values, and each of those values is going to have a different probability of occurrence. Okay, so a little bit dipping back into our quantitative space. All right, so limitations of Hadoop. Now, the direction that this presentation is going from a case study perspective is it's going to land on saying Pig wasn't fast enough for us. We've got too much data and it can't do the job for us anymore. So they switched over to something called Qbert, and we'll see why it's faster. This also gets into a little bit of the motivation of why Hadoop version 3, which is coming out later this year, is going to come up with a much faster version of Pig and Hive and a few other key components. All right, so limitations of Hadoop and joining the group by. Get a couple data sets here. There's a select sum aggregate, like max or min. So just look at this sum aggregate phrase here as being some aggregate function. It takes a set of data and condenses it down to one number. One number is an average over 1 million records, or it's also one number over an average of 10 records. You wind up with one number at the end of the day with an aggregate function. All right, so this specifically comes out and says, do an inner join from A to B on some field. Okay, so this joining group by is awkward because there's a loading of the data, a shuffling, and a reducing to do the inner join and store the output. So these are a lot of steps here. Load, 1, shuffle, 2, reduce, 3, actually do the inner join, 4, do the store, 5. So I got 5 steps. I'm hitting the disk 5 times just to process this. And in the raw data storage format that's available to Pig from HDFS, that causes slowness. So Qbert comes along and says, it comes up with a solution. This isn't going to add a lot more to what we just looked at, so I'm going to skip past this, but it's in another Pig script, basically similar layout, load group for each column store. So the main point is at the top of that slide, obviously, though, large amount of data to shuffle from mappers to users. So like hitting the disk 5 times. Like, can I do that more efficiently? So this is where Qbert comes in. So Qbert is also open source, and it's specialized in processing graph data. So it has a special storage mechanism in it such that we get fast and scalable primitives for joins and aggregation. So it just turns the algorithm inside out and says, I can provide something that's 5 to 60 times faster depending on the nature of the data. Right, so Qbert design, go into Qbert, it's got a scripting language, just like Pig or Hive is a scripting language. The execution is a little bit different. It's not map and reduce, map, shuffle, reduce anymore. There's a shuffle, a block generation, a combine, and a pivot. So this pivot at the end is what gives it a lot of good, solid performance. So we don't need to go into the details of like what are all these things. The concept here is that they're not using map reduce, map shuffle reduce. They're using a different paradigm of being able to manipulate a large amount of data. So if you look at the languages then, in the diagram here on the right, you got Pig and Hive, you got Qbert. Qbert is more of a physical language because it knows about the storage properties, whereas Pig and Hive do not know about the storage properties.
Hive is storage. Pig is scripting, right?
Both of them are scripting.
But Hive is more related to storage than Pig, or how does it work?
Hive overlays a metadata viewpoint. Let me answer the question. This is timeless. This is good. I'm glad Sergio asked the question. Let me go to the whiteboard to do that. Okay, when we look at this diagram, I'll probably have to redraw it in order to answer the question because this is architectural layers, not processing, runtime processing.
Right.
Those are different animals completely. So if I look at it from a runtime processing perspective, you asked about Hive, and what was the other one?
Pig.
Hive and Pig?
Yeah, those are the ones we have there.
Okay. So Hive is, and you're asking in the context of
Right.
storage?
My question was, is Hive more related to storage of data other than data manipulation like Pig, or both are the same, or both have an equivalent percentage of data and storage manipulation?
Got it. All right, so from a manipulation perspective, these are functionally going to be the same. But this is same as in, I do it through SQL, meaning relational algebra.
Okay.
And Pig says, I don't care about relational algebra. I'm going to do it my own way.
Yes.
And it does it through this load and then like filter or group for each, etc.
Okay, all right.
And
So,
then goes to a store command. Okay, so SQL in here, we're going through essentially a reading operation, which is based around select.
okay, so from the end user perspective, Hive will be easier to use, right?
For
Than
people that
Pig.
already know SQL, yes.
Right. Oh, okay, okay.
And it would be more based on the data that one is working with, right? If it's unstructured, probably Hive wouldn't be the choice to.
Right,
use.
so to the point that Juan is making, so when we get to the storage layer that we're putting up here conceptually, Hive says, I'm going to prescribe the metadata. So from a DDL perspective, data definition language perspective, it's going to create the table metadata. So this is the column, what is the name of the table? What is the name of the columns? What's the data types of the columns? That type of information. So this all gets stored by default into, remember the database I mentioned before lunch probably? By default, this metadata gets stored into a database. So this is where the storage element comes in. It's Apache Derby. Derby is a really, really small, lightweight, efficient database. Okay, so that the metadata can get stored in, by default, is going to get stored into Apache Derby. Could be stored into MySQL, anything. Okay. All right, so there's a layer of storage here that is not present in Pig at all, because it doesn't need the metadata. It carries the metadata with it in this context. So metadata is up here, dynamically being created, assigned, tracked. And what's really interesting is that the schema, the metadata, it stays associated with the data itself. Every time a line of Pig executes, it creates a new relation, and all of the schema from the previous relations stays in place. So the schema just grows and grows and grows. Every single line of code introduces an additional layer of schema. You'll see that when we walk through Pig. All right, so the fact that it dynamically, the data is dynamically described, it's a dynamic schema evolution, as opposed to a static schema evolution. So SQL is built around static, Pig is built around dynamic, in terms of describing the data. All right, so these are very different. And then the storage here is still going to be like HDFS or HDFS. Okay. So we didn't put in there processing, but if I'm looking at the processing layer right now in Hadoop version 2, the processing layer is going to be Yarn working with MapReduce version 2. And over here in Hive, I can have the same thing. I'll just have to abbreviate this. Or I can use Spark in the future. Not now. Right now it's Spark. Let's see which one is it now. I'd have to go look that one up. There's a lot of different combinations to keep track of. And in my mind, I'm thinking about a different component that's not Hive. That's what my mind is focusing on.
Okay, thank you.
Yep. So Qbert comes in here and says, I'm going to follow a different pattern here where I'm going to know where the processing language is going to know something about the physical storage. Whereas Hive and Pig do not know anything about the physical storage of the data sets. Qbert comes in and says, I'm going to be intimately acquainted with how that's stored. Back to the screen. Full screen again. There we go. All right, so when you look down at the storage layer, shown on the bottom right corner here, there's Qbert block storage on top of HDFS storage. So this purple region of Qbert block storage is a specific layout of data in a sorted, pre-sorted format, pre-sorted layout that Qbert can then take advantage of because it knows enough and controls enough of the physical storage of the data. Whereas Pig and Hive don't have that level of specific control.
Who owns the Qbert?
I would have to look that up, but it's open source. It's just another solution that's out there. There's dozens of solutions out there. Qbert is yet another one. It's just not popular enough to be included in the certification exams. Pig is bedrock normal processing because it takes such a few small number of lines of code to process a huge chunk of data. Huge meaning like petabytes. All right, so here's a script, a Qbert script. This is just counting daily and weekly stats. So it's the Qubert script sets up the job for create blocks. If you go down to the next one, a job for compute cubes. So there's cubic analysis that's provided by Oracle. And so some of this concept of how do you work with rapidly processing cubic data is drawn off of the relational database world and re-implemented in an efficient manner on a big data solution, in this case in the Hadoop solution. So we don't need to walk through all of this because this is not something that we're going to use. It's not something to get certified on. But the information's in here. The key aspect of cubing from a computational perspective is that there is aggregation and counting and summing going on. And eventually there's a storing at the end of the day. Because whether it's big or Qubert, it's going to end with storing the results. This is storing into a certain file location, directory, file name being results, using a format for Avro, using the Avro format. There's a different presentation that I found that has all of the performance comparisons of Avro and Parquet. So when we look at that, also next week, because I do that in conjunction with the Pig Lab, we'll be able to see, oh, when would I use Parquet? Oh, when would I use Avro? Right. So that it's not that you use one, that one's better than the other, they're different from each other. So Qubert comes in then and allows a faster join and group by. We're not going to look at the details on here because we're not trying to understand all of what goes in. But essentially, if you look at the Qubert join and group by, it really is not any different than the big one. It's the exact same layout of lines, phrase for phrase, word for word practically. Okay, but it's the underlying way in which the data is stored on disk and how it's managed in memory. It gives it huge performance. So I'm going to skip through this. All right, so here's the summary from a statistical perspective. Pig and Hive is indicated in the gray bar, Qubert in the brown bar. So from a statistical calculations, in terms of mean and variance calculations after joining data sets with 70 billion and 270 billion records. So just some loose pocket change in the IT data storage arena of LinkedIn. Okay, but this is their real life back in 2015. It took 40 hours for Pig to go through this because of using the map reduce, shuffle, sort, and everything else, and hitting the disk so many times without being privy to the forcing the storage into a graph-friendly way of manipulating the data. So 40 hours reduced to 1 hour, 6 hours to 10 minutes, 20 hours to a half hour. So exceedingly fast. All right, so there is some additional information in here, not necessarily related to Pig at all, or just this overall environment. But while we're in the study here, we can just look at SAMHSA and Spark. SAMHSA is similar to Spark. Or sorry, which one is? It's not similar. It is similar. Let me get into this one. All right, so SAMHSA is streaming computations. So on top of a message layer like Kafka is where it runs. So if you look at Kafka and it has really low latency and it's extremely fast to do computations in terms of accessing the data and providing the information and stateful processing through a local store. So it doesn't lose track of state. Anything that's web services loses state, trying to design web services to ignore state. So the use cases for SAMHSA is site speed monitoring and data standardization. So just speed monitoring, that's in terms of their own analytics about am I servicing my web pages for whether they're being used sufficiently or not. Data standardization, I'm not privy to what LinkedIn considers to be data standardization, so I don't know what that is. Site speed monitoring. This is how fast can each of the components come up on the web page. So this is a little bit more detailed. Specifically, it's each of the components. So get unread message counts, get people you may know, get pulse news. All of these gets are being executed in order to populate each of these regions on the web page. So the SAMHSA is used for site speed monitoring, meaning how long does each of these individual gets take in terms of processing time. So these are all gets associated with services, one get per service. That's what the bullet is referring to. LinkedIn homepage is assembled by calling many services. Then each service logs through Kafka what went on with the request ID. So in order for SAMHSA to get these stats, it gets it through Kafka. So SAMHSA is a consumer of stats information for each of these gets, each of these services. So SAMHSA's site speed monitoring looks like this from a block diagram perspective. You got the front end service all the way into the data systems, and in between you've got service calls. So there's an architectural layer, 4 layers right here that are shown. And for proprietary reasons, I'm sure they're not going to tell us anything more than that. We've got 4 layers, take our word for it. Go on to the next slide. Okay. All right, so this is a little bit hard to read, but here's a page view event that maps into an unread message service call, a get people you may know service call, an unread message service call. So there's a directory relationship between one event cascading into multiple other events. So there's a sense of what's the overall time from left to right across this tree that's being shown left to right as opposed to top to down, and what's the time within each of the services. All right, so Hadoop, MapReduce, join the logs using the request ID once a day, too late to troubleshoot any issues. Okay, so bring in SAMHSA. We need a near real-time analysis. Can I get the actual experience of what's happening in terms of performance now as opposed to tomorrow? MapReduce says, I'll give it to you tomorrow. And LinkedIn says, I don't like it yet tomorrow. I want it now. So they came up with SAMHSA to do that. So it's a real-time join of the Kafka logs. So remember, the providers to Kafka are giving events. And the key field, the primary key field, if you want to think of it that way, for every single one of these logs is always a timed date stamp. These logs are organized under topics. Very, very flat organization of topics. Okay, so near real-time join, that statement gets repeated up here because we're just kind of continuing. There's not enough real estate on the other side, so this is 2 slides together. In order to do the near real-time join, we partition the Kafka stream by request ID. So this partition means this is the broker. Kafka has brokers. Brokers are responsible for doing the partitioning and maintaining the partitions of which events are going into which buckets, so to speak. And when we get to Spark, to do the, basically with SAMHSA, we've got the ability to look at the stats quickly based off of Kafka logs. Get into Spark, there's 3 topics to cover here. So limitations of MapReduce, and this is plain vanilla stuff. Everybody knows about why Spark is better than MapReduce. So it doesn't matter whether we're looking at LinkedIn slides or somebody else's presentation on these topics of Spark compared to MapReduce. The message here is going to be the same. All right, so limitations of MapReduce. You look across here, file system read, file system write, file system read, file system write. That's the pattern for MapReduce. Every time MapReduce does a job, whether it's a map job or shuffle job or reduce job, it always writes its output to disk, period. Because the goal for MapReduce is to be fault tolerant. In other words, you can resume processing, you can resume the batch processing immediately at the point of failure. You don't have to back up to the beginning of the batch process and reprocess all of that data. Okay, so that's why it's very intense on the read writing. However, that obviously makes it very slow in terms of the time from start to finish. All right. So this is the nature of MapReduce. A little bit more on MapReduce. This is that logical regression model that's being used at LinkedIn. So let me flip by some of these. I'm going to get into Spark here, talk about architecture of Spark a little bit. So Spark extends a programming language of the distributed data structure, and it mentions these RDDs, resilient distributed data sets. So the RDD, and I mentioned this earlier, but what is in the RDD? I've only mentioned it once, I don't expect you to necessarily remember it. between the 8 or 10, those online as well, what's in the RDD?
Redundancy?
Not redundancy. As opposed to, so this is the key point to camp on for a moment. Remember with MapReduce, we said it's all of this, it's saving the data, saving the data, saving the data. So you got large amounts of data being saved. Spark comes in here and says, I'm not going to save the data anymore. I'm going to save what it said.
It's going to save the commands.
Right, exactly. It's going to save the commands. So the RDD, meaning these resilient distributed data sets, those are commands. The only thing that's in those data sets is the commands that were executed by the job. So the idea is that if I hit a failure point during the processing, I can just rerun the commands because it's less expensive to go rerun the commands than it is to write all of the intermediate results to disk and read the intermediate results from disk. Right, so this is a key concept, RDD versus write every single piece of intermediate data to disk in MapReduce. That makes sense? Okay. This is a good interview point. Somebody asks you, what's the difference? Well, why would I use Spark? Yeah, that's the answer. The other answer is that it can be stored in memory. So you actually have 2 points to the answer for Spark. Spark doesn't store it. Under default configuration options, Spark will not write out to disk the data. It can keep all of the data in memory, all the intermediate data in RAM memory. But if your program that's running the Spark job wants to say, wait a minute, I need that particular data set to stay around, the program can override the default behavior of keep it all in memory. And the program that you write can instruct Spark to say, do a store after this particular command, after this set of transformations that's been going on. All right, so lots of APIs, Python, lots of key APIs, I should say. There's Python, Java, Scala is the language that comes with Spark. So what you could write in, like Pig, for example, in 10 lines, can be written in Scala in about 3 or 4 lines. So the idea with each of these higher level languages is that the number of lines that you write gets smaller and smaller. Okay, obviously there's a diminishing point where it's not going to get smaller, but Scala might be at it. All right, so Apache Spark is the processing engine, a distributed operating system. And some of the components on top of it that we saw in a similar diagram where we talked about stream architecture versus batch architecture in the big data analytics class. And here's a little clip of what one one portion of the stream architecture is. Okay, so now we're running this logical regression model on Spark instead of MapReduce. Intermediate data is stored in memory much faster than MapReduce, which stores it to disk constantly. It stores intermediate results to disk constantly. So the key item here is on the right, where it says intermediate data is in memory. Your major point of distinction. Now, getting all this data out and accessible for other services, now that we've gone through all the processing and transformation, the egress part where you get it stored, they use a key value store called Voldemort. This is similar to HBase or other key value oriented databases that are columnar in nature. Amazon has a DynamoDB service. So if you look at their particular high-level architecture, the Voldemort is working with batch jobs associated with Hadoop, and the People You May Know service is working with get recommendations that are drawing data from Voldemort. Right, so this is a really, really common type of pattern where Hadoop is still engaged, but it's just not the main interface. And we saw that with Qbert. Qbert was had storage capabilities sitting above Hadoop. Voldemort has storage capabilities sitting above Hadoop, meaning above HDFS, I should say.
Excuse me.
Yep.
How is EMM or ADMM used there?
It's not used here. It's
A couple of slides
its
before.
output gets stored.
Right, ADMM.
Right. See, the output of ADDM gets stored there. So ADDMM gives that binary, it provides the logistics of yes or no, how many yeses.
So the ADMM is not the algorithm.
It's the algorithm for the logistics regression.
Okay, so that's
In order to predict how many yeses or no's that you're gonna get, and what's the percentage of error,
Okay.
whether that prediction is reasonable or not.
Okay.
And there's dozens and dozens and dozens of those types of predictions that LinkedIn wants to be able to make in order
Okay.
to minimize their data processing.
All right, because I was thinking about ADMM from Stanford, because Stanford is the one that actually produced
provided
the algorithm.
Yep.
And it's normally used to resolve highly complex problems by making them smaller, dividing them in smaller parts,
Yep.
which is okay. All right.
That what you just described, that is the nature of getting to a binary yes or no. You gotta get it divided into really small parts. But how to get it divided so you have reliable output at the end is tough.
Okay.
So this consensus computation here, this is what's getting stored in the Voldemort database. So it's the output of the ADMM processing. The output is this consensus computation. This consensus meaning what's the final result of the model? Is the model telling us high probability of a lot of yeses or high probability of a lot of no's?
Okay.
So this computation is what gets stored in the Voldemort. This is where the end process data goes. Remember how we looked at that one slide that talked about in the big data analytics, we got data acquisition on the left, we've got like Kafka channel in the middle. It's stores the data in the HDFS, the file system for Hadoop. Surrounding the file system of Hadoop, there is the processing by Pig or Qbert in this case, and a few other things. And then that result actually gets stored into yet another database like Cassandra, in this case Voldemort. So you have this progression. Now flash that slide on after we get through the LinkedIn here. And we might actually be pretty much, well, we're almost done with this, so I'll just take it through to the end. Let's see, some more streams on here. I'm not gonna go through this one doesn't, it was just another slide somewhere or the other that streams oriented. All right, so bottom line out of here, rich primitives for data ingress, processing, and egress. Rich primitives means don't have to write very many lines of code. The primitives in the language are very powerful, so I don't need to write many lines of code. Okay, data ingress, Kafka from a extract, transform, load perspective is where, which is interesting because the messaging service itself was providing the input into the statistical computation that Stanza was using. All right. Various forms of data processing, batch is where Hadoop and Kubert fit in. When I say Hadoop here, they're really big. Okay, so this is big in Kubert. Stream processing using Samza, iterative processing using Spark. So this is a summary of what the LinkedIn environment was from a big data viewpoint in 2015. So I'm sure it's changed a little bit, but this bottleneck of using Kafka, or bottleneck, the elimination of the bottleneck by using Kafka, that was like gold mine to them. Okay, so future opportunities, they're looking at other models of computation. You know, they're trying to model their computational, their use of computational resources, memory and disk. So they get efficient graph processing, meaning they're finding ways of making money, relating variables to each other. You want people to say yes to whatever you're presenting to them. Distributed machine learning is artificial intelligence. Okay, so the ending point here, when we look at that left to right where I mentioned the data acquisition, 506 here. To this point, this will look familiar to everybody here. All right, so I have data sources on the left. I've got some type of data collection like Kafka, providing a channel over which the data in motion can be streamed. And Samza is right here. So there's processing of data in motion that Storm and Spark Streaming and Samza each provide. I could use any one of these three components. LinkedIn uses Samza, and it needs to still store its results somehow. So we can actually store it back as events in Kafka, meaning it's still going to stay as data in motion, and the analytic tools have to pick it up right away. Or Samza can store its results, you know, like of that logistic regression. You can store that logistic regression results into Cassandra or Elasticsearch or any of these other components that are will capture the data and leave it in place for analytic tools to process it later.
Okay.
So back into the big data mindset.
It's too much.
I'll send out this link as well as the videos.
Thank you.
But there's a lot of pieces to this thing. So when we focus in this class on the certification that Hadoop is looking for, or that Cloudera offers, the certification is oriented around, well, how do you actually do the data crunching? You know, and as you saw from Kubert and Pig, it was almost like the same lines of data. You know, Kubert had some very specific program blocks in it, but it still was a very, very tight, small amount of code and similar in concept to what was in Pig. So if you learn Pig, then you're equipped to be able to quickly assimilate any other similar pattern of language.
So you need to know all these language?
Nobody can ever know all of them.
Us.
So you pick one, learn it well, and know how it relates to other languages without needing to actually use a lot of the other languages.
But if you do a CCP, then you need to know.
Now, CCP will require more of how to work with this environment that's shown on the screen. But CCP is not gonna say, well, you can do it in Pig, now let's see you do it in Kuber. It'll say do it in Pig and show how Pig relates to HBase and Hive, for example. Because Pig can read the schema for, let me go to the whiteboard and we can close on this point here.
CCP actually test your skill on Cloudera, its own ecosystem, right?
Yes,
So whatever end-to-end in their ecosystem, then you need to know.
that is exactly right. So Pig, I wrote this as a vertical stack here separate from Hive. Pig can actually read, or load, I should say, using schema that's defined by Hive. So there's a H catalog, it's called. So technically this is this space right here where we're adding in the metadata. It gets stored in the Apache Derby. Yeah, this item here, I'll go -9, so it's hopefully not confusing. This is referred to as the H catalog. I think I spelled that right. It's pretty close. So if Pig is reading in data files that are complex, meaning there's maybe a dozen fields in the files that are being read in, that's a lot of extra schema to put in the Pig script itself. So instead of putting it in the Pig script, it can be, that schema definition can be stored in the Hive catalog. This definition of the metadata is the Hive catalog. So there's some interaction across the two, right, in that sense. All right, so next Saturday, we'll have cleaned up machines here. And we'll dive into Pig right away in the beginning. There's some concepts that will be refreshed in our mind, like relations, tuples, this idea of data processing from a load, group by, filter, but we'll go through all of that. And I don't provide, like in the SQL class, I provide the scripts there because everybody's really oriented towards the certification here. You gotta type these things in with your fingers or get it to stick in your mind. So don't provide any scripts. Just go ahead and work through the labs. So I've got some notes on how I'm adjusting the sequence of the labs. So since we didn't quite get to start with Pig today, I wanted to, we had our lab issues. I'll actually give you a little bit of time to give you some additional notes to go with the Pig lab. We kind of straighten out some of the old notes in a little bit more usable fashion. So I've been able to talk my way through it just fine in the past. I got notes for it, but having something written, let's just save us another extra 5 or 10 minutes next Saturday. All right, so
I have a question.
Riley,
Whenever you have a minute, you'll have to see mine.
okay, so I'm going to close off the broadcasting here. I'll just